What is up? This is our Physics 2 Lab 6. Faraday's Law. This is our final lab. So let's get into it. For our table of contents, we're going to have an introduction, go through the physics principles, the experiment procedure, the experiment data, computational model showcase, interpret the simulation, assumption, source of error, discussion questions, and then the conclusion. So to start off, the purpose of this lab is to study the magnetic induction and currents by analyzing observational data of a bar magnet falling through an aluminum tube, and then create a computational model to simulate this and compare results. Our main physics principles in this lab are Biot-Savart law, Faraday's law, Newton's second and third laws, and the outcome is that the experimental time was 1.15 seconds, and the computational time is 0.8 seconds. So for our physics principles, Biot-Savart law, this is a steady current produces a magnetic field around it, and the strength is based on distance, which is this r squared right here. Faraday's law, a changing magnetic field through a loop induces a voltage proportional to the rate of change of magnetic flux. This is from our formula sheet, so this would be the voltage, and then right here is our change in magnetic field over flux. So there we go, or magnetic flux over time. Newton's second law is just net external forces equal to change in momentum over time, so delta P over T. And Newton's third law, don't need an equation, it's just equal and opposite reactions. So for our experimental procedure, this is going to be the video down here. We have our system, which is a bar magnet and an aluminum tube. The surrounding is everything else. So we're just going to drop a magnet through the tube, just like how this video is. So drop through, boop, comes at the bottom. And then you record this for 5 runs and just kind of took the average. So as you can see, as this falls, it creates a current that spins, which is going to cruise the magnetic field, which is going to push it up, resisting the force of gravity. For this data that we recorded, we took the mass of the magnet, we recorded 5 times, and we found the average to be 1.154 seconds, so I rounded that to 1.15. And then we also took the dimensions of the tube, so the length of the tube, the foil width, the inner and outer radius, and then our magnetic dipole moment. This is from any previous lab. And we're using the same types of magnets, so it doesn't matter. For our computational model, first, the initial conditions, we kind of just leave these the same. We're just plugging all of this over here in from the previous slide. And then these, so magnetic field of a bar magnet, we have this from a previous lab. So you can just plug this equation in. This is your general form of the equation. Flux was a brand new equation, but once again, I kind of go back here, basically just taking this equation and taking what you have in code and creating it. So it's like, oh, well, have this, get a speed. I mean, you just literally just plug this stuff in. So yeah, it's just turning computational model from what we know, the answer formula sheet. Anyway, same thing for the forces. I'm pretty sure we all probably have roughly the same code since these equations have to look similar. So just going to leave this here, but mainly just know F net is F grav plus magnetic. And remember, magnetic and grav are going to be opposing each other. So here's what we get for the output, right? This is the final output after it's falling out the model, but while it's falling, imagine this blue here and this red here just kind of comes down. And then we have our we have our graphs. We have where its velocity kind of increasing down, stays the same, and then increases. This is our output of how long it took, which was 0.8 seconds. So interpreting this, which color corresponds to counterclockwise and clockwise? Using Lenz's law, we know counterclockwise is red and blue is counterclockwise. So just think about how it was falling and what was opposing which. If you flip the magnet, it would just change the direction of the current. How does real-world data amount compared to the computational model? Computational model is shorter, and this is probably due to some things that we aren't accounting for, like resistant friction, which we'll talk about on the next slide. How does the plot shape? So what the plot shape tells us is that right here, gravitational force is greater than magnetic force because it's increasing down. And then once we hit the middle, it actually equals out and velocity stays constant until then. So top of the tube, and then bottom of the tube is where it is. Gravitational force is stronger. So for our assumption source of error, our assumptions are that negligible air resistance, bar magnet acts as a magnetic dipole, and the only forces on the system are magnetic and gravitational forces. And our errors are stopwatch timing and precision, inaccurate magnetic dipole moment, friction from the magnet hitting the sides of the tube and slowing the magnet down, and air resistance falling the magnet down. For our discussion questions, what if the resistivity of the conductor were reduced as close as possible to 0? Would the dynamics of the falling magnet change? So from Ohm's law, we know V equals IR. So by decreasing the resistance, we're increasing the induced current, right? Because V is staying the same. So R decrease, I has to increase. This produces a stronger magnetic opposing magnetic field, which would slow the magnet down more. Now, what if we cut holes or slots into the tube? Well, this decreases the overall current of the tube, right? There's less foil. So this would produce a weaker opposing magnetic field, which causes the magnet to fall faster. And just a quick little conclusion here. Faraday's law, it explains how magnetic forces can cause induced currents. By studying these forces, we can understand this natural phenomena. We can actually apply this experiment to real-world scenarios, allowing us to see more practical such as Faraday's law, such as motors, something like that. So thank you so much for watching. This is the last lab of the year, and that'll conclude it for Physics 2. So thanks.